Hello everyone, my name is Daniel Rupp and I will present the paper called SATOR, Seamless 3D Teleportation to both ground and mid-air targets. For traditional target selection-based teleportation, target points are usually restricted to intersection points of a straight ray or a parabolic arc with the scene's geometry, not allowing users to select mid-air targets in order to observe points of interest on other elevation levels, to get a quick overview of the environment, or to navigate more efficiently around larger obstacles. Most existing mid-air selection techniques use a form of ray cursor, so a straight ray that is emitted in the forward direction of the controller, together with a cursor that moves along the ray. The distance of the cursor along the ray can either be specified by the controller's touchpad or is automatically determined by the system. However, none of them consider navigational requirements like staying at the same elevation level, ground-based movement, or transitions between ground and air or vice versa. The technique from Weisger et al., which we will refer to as elevator, considers these aspects. Their approach requires the selection of a ground point first before moving it into the air. So the accuracy of the final point in the air is dependent on the ground point. Therefore, this twofold approach is less accurate and slower than the ray cursor approach. To combine the advantages of all previously presented interaction paradigms, our work in this paper proposes a combination of the fast and efficient approach of the ray cursor method with the consideration for ground maneuverability similar to the technique proposed by Weisger et al., by following a two-mode paradigm, a ground and an air mode, where the system transitions dynamically between them based on the user's behavior. For the ground mode, we implemented a straight ray and a parabolic arc. In air mode, we used the ray cursor approach from related work with either the joystick or the controller tilt for distance control of the cursor along the ray. With the ray ground tool, the target point is determined by the intersection point of the ray with the ground geometry. If the ray no longer intersects with the ground, the system transitions to air mode, allowing mid-air targets to be selected. While the straight ray is generally less ideal for ground movement, the transition to air mode can be done seamlessly. A parabolic arc, on the other hand, provides greater accuracy than a straight ray and also allows users to jump over small obstacles or onto small adjacent platforms. However, transitioning into the air is less straightforward, as tilting the controller up would still curve the ray towards the ground. Therefore, users have to manually press a button when they want to transition into the air. While this adds complexity, it also allows the user to trigger the ground mode while in the air to select targets on the current elevation level. When in the air, we implemented two distance control mechanisms. With the joystick distance control tool, similar to related work, the depth along the ray can be determined by moving the joystick back and forth. This works simultaneously while aiming. To transition back to the ground, simply slide the preview avatar on top of ground geometry to land on it. After landing, the system automatically switches to the ground mode for further navigation. The tilt distance control mechanism follows a two-step approach where users first have to aim in the intended direction and lock it before the tilt angle of the controller determines the depth. Similar to before, in order to transition back to the ground, users can simply slide the target location on top of standable geometry. Finally, we adapted the original implementation from Weisger et al., for which we had access to the source code, to make it visually similar to our SATOR techniques. Our research questions and hypotheses can be boiled down to two simple questions. First, will SATOR in general outperform the elevator technique? We analyzed this by averaging the results of our SATOR techniques and performed a t-test. Second, which variation of SATOR will perform best, which we analyzed using a 2x2 factorial repeated measures ANOVA. In our user study, we had a total of 30 participants between 21 and 33 years old with mixed VR experiences. We then tested 5 conditions, our 4 SATOR variations and the elevator technique from Weisger et al., in a route following task where participants had to follow and activate a set of cameras. During the user study, we logged the route completion time, the overshoot, which is the difference between the total teleportation distance and the length of the route, so a value of 0 indicates that participants teleported very accurately towards the waypoints without any overshooting, the number of teleports, and the average specification time. When comparing the average SATOR technique to elevator, we found that the average SATOR technique had a significantly lower route time, less overshoot, and required fewer teleports, while there was no difference for the specification time. These results are in line with what we expected, since the elevator technique required participants to select a point on the current elevation first before moving this point into the air, so aiming was a lot more difficult, resulting in more overshooting and requiring more teleports to backtrack and ultimately increasing route time. When looking at the different SATOR variations, there was only a significant difference for route time, where the straight ray and the joystick were significantly faster than tilt. For questionnaires, we used the User Experience Questionnaire and the NASA Task Load Index. Here, the average SATOR technique showed a significantly higher efficiency rating and lower task load. When looking at the SATOR variations, the straight ray showed significantly higher perspicuity and lower task load than the parabolic arc, while the joystick showed a significantly higher dependability score. In terms of user preference, elevator was only twice voted as best technique, while most rated it as worst. Regarding the SATOR variants, we can see a clearer trend towards the straight ray as ground tool, while the preference for the distance control is somewhat even, with straight ray joystick and straight ray tilt conditions being named as best techniques an equal amount of times. However, joystick has slightly more second and third ranks than tilt. Finally, our results showed that SATOR in general improves over the baseline in terms of efficiency, usability, task load, and preference. As a result, we suggest offering a variation of SATOR when users should be presented with the option to gain an overview of the environment, observe environmental features at different heights, or maneuver quickly around larger obstacles. For the specific SATOR variation, we recommend using a straight ray as ground tool since it is faster and easier to use. For distance control, it is harder to name a clear winner as there were not a lot of differences between them, and it is mostly dependent on user preference. When designing SATOR, we had to choose various parameters like the maximal tilt angle or the speed of the joystick. The selection of these parameters was based on internal testing, which leaves room for further optimizations, and potential shortcomings might influence the results of their respective features. In addition, we did not consider rotation specification, which is also a common feature of teleportation-based navigation techniques. Because of the large number of conditions in our user study, we only considered a route following task, which only offers one perspective on the use of the tested techniques. Although we made sure to cover a vast amount of navigation scenarios by carefully placing the waypoints, a more open task design like an uninformed search task would make our results more generalizable. Thank you for listening to this presentation. If you have any more questions, feel free to reach out to me or my colleagues.